Okay. Metalloids. What's this word brittle mean? If you hit it with a hammer, it will turn into a powder, right? It's not bendable. You can't bend it. It'll just shatter. Metalloids are solids, and they're not good conductors. They're kind of okay at it. They're semiconductors. They have a high melting point, and they give away or share electrons. Now, that's the most important part. Okay, class? Metals give away electrons. Metalloids give away or share electrons. Okay, this is silicon. All right, Marvin? We make computer chips out of what? Silicon. Is that on the staircase of metalloids, Colby?
Yes.
It is. Silicon's a metalloid. Now, why do we make computer chips out of silicon? Well, because it's a semiconductor. It can conduct electricity. And it also has a high melting point. Well, yeah, but you just told us that copper can conduct electricity. Yes, but copper will do what? It'll melt. Silicon won't. So here's some silicon. Okay, it's nice and brittle. The last type is to the right of the staircase, and those are nonmetals. They could be solids, liquids, or gases. They have low melting points. They're poor conductors. And this is the most important part, Phoenix. They take electrons away from other atoms. These characteristics are the most important. Metals give away electrons. Metalloids can give away or share electrons. And nonmetals take electrons away from other atoms. Those are what determine whether it's a metal or a metalloid or a nonmetal. Those are the most important. Okay? Okay. So, now, those are the three main types of elements. But you also have to remember what the group names are called and their characteristics. Like, for example, Shania, the group names. What is the group 1 called? Alkali metals. Cam, group 2 is called alkali earth metals. The middle part is called what metals? Transition metals. Shania, the staircase is called metalloids. Group 17 is halogens, and group 18 is noble gases. What is the most important characteristics? Which ones are the most reactive on the entire periodic table? 1 and 17. What is the most unreactive on the periodic table? 18. Okay. So did I show you guys a video of the blimp blowing up?
Yes.
Yes, I did? Okay. Who can explain to me why the Hindenburg blew up? They did not use helium. They used hydrogen. All right? Hydrogen is on what part of the periodic table? What group? Group 1. Kennedy, is group 1 go boom? Yes. They use hydrogen in the blimp. Well, because we stopped selling helium to the Germans in the 1930s. They couldn't produce helium, so they just used hydrogen, and it went boom. Okay? Helium does not explode. Why does helium not explode? Because it's a noble gas. What do noble gases do? Nothing. Okay? For example, if you wanted to preserve yourself for 10,000 years, you can preserve yourself in argon atmosphere. So the best way for you guys to be mummies in this day and age is to freeze yourself first and then seal yourself in an argon atmosphere, because the noble gases will not react with you. Okay. Now it's time for some show and tell. So now, guys, go to this thing that says periodic trends, y'all. How we doing, Joe? Periodic Table Trends by Miss Brooke Lynn Powers. She made this presentation. All right, dudes. Atomic radius. What is a radius? Colby, what's a radius? Half of diameter. So that means it's basically the circumference. It's the size, right? as you go across the periodic table, do the atoms get bigger or smaller? I'll tell you what, Sydney, read this thing that says the atomic radius.
The atomic radius is the distance from the atomic nucleus to the outermost stable electron orbital in an atom at equilibrium.
Read where it says as you move. Lexi.
As you move left to right on the periodic table, the atomic radius increases.
Okay, so you have to memorize that. That's one of your secrets you have to know. They actually get smaller. Now, why do they get smaller? The reason why is because the nucleus is positive, the electrons are negative, and the nucleus pulls the electrons closer to it. Okay? But as you go down, you add more layers of electrons. You know, like an onion? You ever heard of ogres like an onion, Joaquin?
Yes.
Okay. So, you ever seen layers of an onion?
Yeah.
Okay, so if you add layers to the onion, it gets bigger. Same thing as an atom. If you have layers of electrons, you get bigger. So that's what happens as you go down. So as you go down, class, the size of the atom gets what, Shania? Bigger. Okay? All righty. Now, go to the thing that says ionization energy. Go to the slide that says ionization energy. And read the slide, the definition, please. No better than Tristan, of ionization energy.
Ionization energy is defined as energy required to remove an electron from a gaseous atom.
Okay. Required to remove an electron from a gaseous atom. Read the definition where it says high ionization energy. Colby, a high ionization energy value.
A high ionization energy value indicates the atom has a strong hold on its electrons. Atoms with large ionization energy values are less likely to form positive ions. Likewise, a low ionization energy value indicates an atom loses an outer electron easily.
Okay, dudes. We're going to do an experiment. Are you ready?
Yes.
Okay. I'm going to prove to you. We're going to watch the ionization energy decrease as we go across the periodic table with some real elements. Okay? Everybody go find sodium on the periodic table. Sodium, please. Now, based on what we is sodium a metal, and will sodium give away electrons or take electrons, Lexi? Give away or take away? That will give away electrons. It will give away electrons very, 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 very fast. Okay? It will give away electrons very fast. And just like I'm going to break this projector very fast. Yay. Hooray for HDMI. That is awesome. Power off. Well, whatever. You guys can see up here. Okay. Sodium. Now, did I do this Tuesday?
Yeah.
You want me to do it again?
Yeah.
Okay. Sodium is in group 1. What is characteristics of group 1? Do they do explosions? Yes, they do. You've got to be able to tell me why they do explosions. Because do they give away electrons easily? Yes. You know they give away electrons easily because they are metals. They also have what's called a very, very low ionization energy. And what that means is it doesn't take anything for them to give away their electrons. They want to give away their electrons. And if I could just cut a piece, that would be awesome. Okay, look at that. Ugh. Oh, definitely don't want to put that one in there. That would be crazy. Okay, so sodium wants to give away its electrons. Because it is in group 1, and because it is a metal, it wants to give away its electrons very, very fast. So let's focus on this. Sodium in the water. Boom. Really fast. Look at it rapidly generate hydrogen gas. It may even spark. You see some sparks? See?
I said you were poking.
Did sodium give away its electrons? So, does group 1 really want to give away its electrons? So what do we learn from that today, from that violence? Group 1 gives away or takes electrons? Do metals give away or take electrons? Give away. Let's move on from there. Sanaya, you scared? Did you sleep through that, Cam? Dude, that was so powerful it cracked my beaker. Look at that. Oh yeah, that beaker's done. Okay, well that's all right. Let's move on to magnesium. Now, based on what we just learned about magnesium, about ionization energy, Colby, you're going to make a prediction. A prediction. Okay? Magnesium, put your finger on magnesium in the periodic table. Is it the next one? It's the next one over. What type of element is it? Alkali earth? Alkali or alkali earth? Now, based on what we just learned about ionization energy, will this one take electrons, give away electrons just as fast or slower? It will give away electrons much slower. Here it is in some water. I'm just going to drop it in some water. Ready? Boom. It's going to blow up. Oh my God, boom. Boom. Nothing. Literally almost nothing. Okay? It'll take a while, but it'll eventually react. So why is there such a big drop-off from sodium to magnesium? Because look at the trends. It says ionization energy does what going this way across the periodic table? It increases. It becomes harder to make it go boom. Because it does not want to do what as fast, Lexi? Give away electrons. Okay, well, what if we stay in the same group? What if we go down to calcium? You know, calcium, strong bones, healthy teeth. Calcium, strong bones, healthy teeth. Use your information to make a prediction, scientists. If you go down the periodic table to calcium, will this give away electrons more easily or not? It will. Because, what does the ionization energy trend say? As you move down the periodic table, it does what? It decreases. Ionization energy decreases. So if we have just a bit of calcium, what will happen is it'll start generating, not right away, but eventually, some hydrogen gas. You'll just see some fizz-fizz. It won't be that exciting, but it'll be present. Okay? This thing is cracked, so I don't know if it'll... All right? Nothing really exciting at first, but you'll start to see it pick up pace, and it'll generate some hydrogen gas. You see the bubbly? Is that even close to being as fast as sodium? Not even close. So why is there such a dramatic difference between group 1 and 2? Because group 1 likes to do what? Okay, now you moved over to group 2. So if group 1 loves to give away electrons, and you move over to group 2, do they give away electrons as fast as group 1? No, they do not. Okay? All right, well, let's move to the middle of the periodic table. Everybody go find zinc. Go find zinc. Let's try some up some zinc and some water. I have my little Tupperware of water here. Yeah, I'm generating some hydrogen gas. Ooh, check it out. Watch. Prove it to you. Here we go. Look. No. They're just little bubbles of hydrogen gas, but they're working. Nothing that exciting, though. Okay, here we go. Water and zinc. Oh, this should explode, shouldn't it? I mean, this should go boom, right, Oros? Boom! Did that go boom? 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 Yeah, look at that. Calcium picked up the pace, didn't it? I'm not going to light. That's the same flammable stuff that you just saw, okay? So it's the white stuff is calcium hydroxide. Calcium reacts faster than zinc. Why? Which one gives away electrons faster? Calcium does. Okay? Now, look, Shania. Look, everybody. Is calcium in the same row as zinc?
Yeah.
Yes. Which one reacts faster?
Calcium.
Why? Because it's on the left, and what does it do? Gives away what? Electrons. Does zinc give away electrons? No, not really, no. Okay? So as we move to the right of the periodic table, what do these things start doing, Tristan? Do they give away electrons, or do they start taking electrons? They start taking electrons. Okay? Zinc doesn't want to give away its electrons, really. Okay? So that's why it becomes less explosive until you get to where, Colby? Group what? Group 17. And then when you get to group 17, and really group 16, then they start taking electrons. They start taking things. Okay? I'll give you an example. This piece of copper. Why does this piece of copper have tarnish on it? Tristan, you're a pretty street smart guy. Why does copper have tarnish on it? What is tarnish? Oxidizing. Oxygen is reacting with this copper, and it is tarnishing the copper. Okay? Oxygen is tarnishing the copper, so it's reacting with copper. Very slowly, okay? But oxygen is taking electrons. All right, so class, group 1 elements, do they take or do they give electrons?
Yeah.
Group 17, do they take or give?
Yeah.
No, they take. Okay, group 1, take or give electrons? Group 17, take or give? Take. What happens when you have group 1 that really wants to give meet group 17 who really wants to take? What happens? Explosion. Okay? That makes sense. Ma'am? Fluorine and cesium? That's exactly what I was going to say. Fluorine and cesium, if you touch those two together, bam! All right? So, go back to this presentation here. And there we go.
Right there is crazy.
What's wrong? Walk in.
Francium and
Can't isolate francium. There's just too little of it on the planet.
Cesium and astatine.
astatine.
No, astatine would be very low to react. Okay? All right, and that I was just about to get to that. Go back to the thing we were just looking at. Okay, so as we go across, okay, you see where it says ionization energy increases? It means it becomes more difficult to make go boom. Which one went boom better? Sodium or calcium? Sodium went boom better because it's very easy. It doesn't take any energy at all to make it go boom. Calcium went fizz, fizz, fizz. All right, that's a little bit harder to make go boom. What did the zinc do? Nothing. It takes more energy to make zinc go boom. And it takes even more energy to make these guys go boom. Okay? Until you get to what group? 17. Now, group 17 is very reactive, but guys, it's not going to give away its electrons. It's going to take them. Okay? Now, as you go down the periodic table, it gets easier and easier to make it, to remove electrons. But over here, all right, astatine is not as good at taking electrons as cesium is. I mean, not as good at giving them away. Okay? All righty. Go to the next thing that says, I'm sorry, back up a slide. Read that definition, electronegativity. Marvin, electronegativity element indicates.
The electric negativity of an element indicates the relative ability of its atoms to attract electrons in chemical bonds.
Relativity of the, okay. And electronegativity generally decreases as you move down a group. Electronegativity values are expressed as items of 3.898 per less. What was the element that burnt the chicken? Fluorine. Do you know what the element that takes electrons the fastest is? Fluorine. That's what that means. Elements over here near fluorine take electrons. They're more electronegative. Elements that are down here near cesium and francium Do they take electrons or give them up?
Give them.
They give them. Okay? That makes sense. Alrighty, how many of you have Clorox or used Clorox before? Have you ever gotten it on your hands?
I wish this thing real quick, get that thing off.
Why does it feel slippery when you get it on your hands? Taquana, why does it feel slippery when you get it on your hands? Huh?
Oh, yeah.
I mean, haven't you ever felt it after you, doesn't it feel a little bit slippery after it gets on your hands? You know what it does? It dissolves a layer of skin. That's why it's slippery.
That's what I'm not feeling. I'm washing that away, buddy.
Yep. It will literally peel layers of skin off of you. And if you ever want to get rid of a body, you get a bunch of Clorox and a bunch of peroxide, and you use them.
And what?
Clorox and peroxide.
Is that how they did it on Breaking Bad?
Yes. No, that was hydrofluoric acid.
Do they pour it on their teeth?
Huh?
What about their teeth? You grind them up and throw them in there. Okay.
All right, thanks, y'all.
You cut their fingers and toes off.
Yeah, and you, like, yeah, so they can
Good
identify.
to know.
They can't admit it.
Pull all the teeth out.
Now you can still identify somebody. You can do it by DNA. It's easy.
What happened to the
Just
Not
feed
as
them
like
to animals.
So why does Clorox dissolve human tissue? Well, because chlorine, does it give electrons or take electrons? Takes electrons. And yes, on Breaking Bad, hydrofluoric acid has one in it. Fluorine. All right, so what have we just proved over and over again today, class? Which ones are the most explosive on the periodic table? Which ones, Oros? One and? Now, why? One does what with electrons? What does one do? Gives. What does 17 do? Takes. Takes. Okay? All righty? Now, I'm going to, electron affinity, go to the thing that says electron affinity. Electron affinity, guys, basically means the same thing as electronegativity. Neutral atom's likelihood of gaining an electron. On the whole periodic table, Lexi, which element is most likely to take electrons from things?
The one that the air is pointing.
No. No, we just discussed it.
Oh, so
It burns bricks, it burns whole chickens. Which ones? Fluorine. Next to that would be oxygen and chlorine. Okay? So that's electron affinity. Guys, I'm going to teach you how to memorize this stuff real quick. Okay, if you go back to this, here's the secret to memorizing all this, y'all. If you write arrows like this in your notebook, and this is how you make yourself study. You draw an arrow and you draw an arrow. And you write atomic radius, and obviously it decreases that going that way and it increases going that way. All the rest of the trends, really you only need to memorize two things. Okay, let me say that again. Oros, as you go down, if you go across this way, what happens to the radius of the atom? Decreases. As you go down this way, what happens to the radius of the atom? Increases. If you know that, Gobi, all of the other things we talked about are the exact opposite. All of them. Ionization energy decreases, increases. Or excuse me, increases, decreases. Okay? They're the opposite of radius. Okay? You gonna write that down? You gonna write it down? You might want to write it down. Okay, do you need to memorize all these trends? Marvin, Winfield, am I going to quiz you on this stuff? Do you need to memorize this stuff we just went over? Do you need to know the characteristics of metals, metalloids, and nonmetals? Do you need to know noble gases in group 1 and 17? Do you need to know about atomic radius, ionization energy, electronegativity, electron affinity?
Yeah.
Yes, you do. You know about all of them. Will they be on quizzes and tests? Yes, they will. Okay? The last thing I'm going to go over, guys, is shielding. Okay? And you guys need to, get a place where you can draw. We're going to draw the Bohr atom when we talk about shielding. Okay, so I'm going to erase this real quick. Hopefully you got this. If you haven't, and you didn't write it down, take a picture of it. Hurry up. No? Take a picture? You got it? Titmus, you got it? Testerman?
Yeah.
I almost called her Testaverde. Okie doke. Last thing, guys, is something called shielding. Joaquin, an ogre is like a... An ogre is like a...
An onion,
Yes, why?
because it has layers.
Correct. Well, guess what? An atom is like an ogre. You know why an atom is like an ogre?
An atom has layers.
Yes. Explain, Joaquin. Explain it to Lexi.
And Shrek, he's like, yeah. Anyway.
Okay, dudes. We're going to draw the Bohr model of the atom. Is you ready? Here we go. There we go. Okay, just draw this and just put the word nucleus. I don't care how many protons and neutrons are in it. All righty. Draw yourself a ring. That would be 1. Energy level 1. Draw yourself another ring. That'd be energy level 2. Draw yourself a ring. That'd be energy level 3. Energy level 4. Energy level 5. How far can we go? All the way to 7. Right? Why only 7, Cam? That's my man. Excellent job. Okay, dudes. So, if you go across a period, do you add on more rings? Uh-oh, what happened, Joe? You good? As you go across a period, do you add more layers to this onion? Okay, if the element is in period number 1, how many rings of the atom would it have? 1. Okay? If you go to period number 2, like for example, lithium or carbon, how many rings of the Bohr atom would there be? 2. What about period number 3? 3. What about period number 4? 4. You see how as you go down the periodic table, you're adding layers to the Bohr atom? This is a Bohr model of the atom. Niels Bohr, the people that we learned about in chemistry class. But, Joaquin Phoenix, same period and go across the periodic table, are you adding more layers to the onion? No, you're not. You're just staying on that layer. See the difference? Want to explain it one more time? Okay. All right, you see how you have 7 layers in the periodic table? Okay. If I go across this way, am I staying in the same period? Yes, I am. I'm staying on this ring, aren't I? Well, if I'm in the first row, then I'm just on the first ring, right? If I'm in the second row, then I'm on the second ring, right? Okay. Does an element in the second row of the periodic table have 7 rings? No. But if I go down the periodic table all the way here to francium, does it have 7 rings? Yes. So what that means is, right here, that's called shielding. Shielding is adding layers. What is shielding, Kennedy?
Adding layers.
So if you go across the periodic table, do you add layers? No, you do not, because you're staying on the same layer. You're simply adding electrons onto the same layer, the same ring of the Bohr atom. E4, row 4, energy level 4. If I add more electrons, they're just going to stay on this layer. They're just going to stay here. Did I make the radius of the atom bigger? No. But if I go down the periodic table, do you add layers? Yes. Then the atom becomes bigger. Shielding. How many of y'all ever seen Captain America? Does Captain America have rings on his shield? Think of it that way, okay? Captain America and rings. Okay, all these trends you need to memorize. Okay? You need to memorize these. Those are the secrets behind the periodic table.